Okay, so good afternoon, everyone. I'm Fernando Tinaut Ruano, a second-year PhD student at the Instituto de Astrofísica de Canarias. And as Alessandro said, I work on the spectroscopy of asteroids, mainly primitive asteroids. Today, I'm going to explain how is the state of our work and how it will be completed with the very useful for us Gaia Data Release 3. But firstly, as there's not much people on asteroid science in this workshop, I'm going to explain a couple of things very fast, just to let you know. Firstly, primitive asteroids are the building blocks of our solar system. So study their composition is the key to track water and organics and other components around our solar system. So how could we derive the composition of our asteroids? The main feature is around 3 microns. There is the main feature to characterize an spectra and the composition of the asteroids. And this region is quite inaccessible, difficult to observe from Earth due to the atmosphere bands, absorption bands. However, in visible wavelengths, as you can see, the primitive asteroid spectra is quite flat in general. We only can see one feature here, that is the zero point 0.7 micron band in in asteroid that is related, but it's not it's not always related with hydration, but it's somehow related with hydration. This one is the only feature that we can see in the invisible wavelengths over zero point 0.5, but we have a huge absorption down zero point 0.5 in the blue near ultraviolet wavelength range. We have to know that different spectral shapes has been already classified in different taxonomies that are named with different letters. I have put here only four taxonomies inside the primitive asteroids. It's important to notice that we have not any systematic spectroscopic study in the ultraviolet of primitive asteroids. So ours is kind of the first one, and when Gaia arrives with a lot, like thousands of asteroids, spectra of asteroids, we are going to have the first serious study on this issue. Okay, how we observe asteroids. Here you can see one image from Hubble Space Telescope wide field camera using a prism but without a slit. Probably you are not going to be able to identify where is the asteroid, but the asteroid is this one. Why? Why is not moving the asteroid, the asteroid that is a moving target? This is because we are following the target. So we have a bunch of moving stars in our field that could cross. If we put one slit here, let's say that we are going to put a slit in the vertical axis, this star will cross sometime the slit, making the background get different. And we have also some difficulties to identify the asteroid sometimes because not always the orbital parameters are very precise. So we have some difficulties in this point. That is that asteroid moves in the sky. We have also one peculiarity in our observation, and is that we are not interested in the light that comes from the asteroid itself. We are interested in how the solar light interact with the asteroid. So what we do is to divide the asteroid spectra by the solar spectra. The problem is that we should have the solar spectra observed at similar air mass and by the same instrument that we observe the asteroid. And the sun is not visible at night. This is not a surprise, but it is not. So what we use is what we name solar analogs or solar twins. Here we have another problem, and is that not not all the solar analogs are well characterized in the ultraviolet, as the main catalogs in asteroids use the visible wavelengths. They are very well characterized in visible wavelengths, but they didn't work in down 0.4 microns. So we have a paper that is proposed to be published in astronomy and astrophysics, where we explore how bad are the results if you don't take the proper solar analogs. In this paper, we re-study a sample of asteroids, and we obtain very different results. We find a lot of F types that are quite strange in the main belt, that were quite strange, but just because we were not able to see to see those wavelengths. And when you use a proper solar analog, you change your slope here, and suddenly some F types appear. Okay, so what we see from the ground, what are our main results right now? We have studied like 70, between 70 and 100 asteroids, primitive asteroids, among different taxonomies. And what we have found is a very nice correlation between the slope change at 0.55 microns that we are going to see in the spectra is around here, how the slope changes from here to here. That, as you can see, there are different behaviors, to positive to negative to flat to negative, and positive to positive also. We can find all of them. So we have found that this change in slope is quite related with the change in slope at 0.7 micron. We have to remember that is the only feature that we can find in the visible wavelengths. So the change, how the slope change in this region is correlated on how the slope change in this region. We have to remember that the 0.7 micron band is related with hydration and with phyllosilicates that has some iron inside. So we could say that it has been proposed already, this relation from laboratories from measurement of laboratories like chondrites and meteorites. And we have now the observations of asteroids that conclude has the same conclusion, that the slope change, the ultraviolet drop, is quite related with the hydration band at 0.7 micron. Another and a new feature is that we have seen that the beginning of the neural ultraviolet absorption has a different wavelength from different taxonomies. This is quite new, it's not already published, but if you look in this noisy region, we could see how the F types begin the drop. Some of the F types, not always, but some of the F types begin the drop at 0.4 microns, in the same way as did some of the B types. However, C and G types begin the ultraviolet absorption at 0.5 micron. We have made some analysis in our sample, and when we were able to calculate this, to compute this wavelength, we already say that it's quite clear that the F types and B types, okay, we have been able to compute this wavelength only for 3 B types, but when Gaia arrives, when we will have 300 times more objects, we are going to see this more clearly, and we are prepared for this. So what are we expecting from space? We are expecting to increase a lot the time, the number of objects. So we are going to be able to see if this trend is kind of an evolutionary track or are different cluster. We could imagine that G types, for example, are here, or that C types evolve to G types, or in the other way, just having bigger sample and populating these plots with more objects, right? We are also very interested in the F types because are different objects, different. We have found that they have lower diameters than the G types, for example, than the C types. So we are beginning to thinking about the possibility that they came from another reservoir of material in the solar system. And we would like to see that this is a cluster, a different cluster, that they don't follow this trend. Another point is that as we are out of the atmosphere, we are going to have a higher signal in the ultraviolet region. This is because the atmosphere take most of the ultraviolet light, absorb most of the ultraviolet light.
Fernando, excuse me, 4 minutes.
Okay, I'm just finishing. So conclusions. Near ultraviolet are key wavelengths to explore the asteroid reflectance spectra and deduce hydration and composition of the asteroids. We have already found a correlation between near ultraviolet absorption and another band related with hydration. We have noticed that ultraviolet has some information to differentiate between different taxonomies, and Gaia will be kind of the key to have more context in our results and more robust conclusions. Thank you all.
Thank you very much. Thank you for this very interesting talk. Perfect timing. Is there any question in the audience or online? It is clear that with the amount of expected asteroids that Gaia will release in about 3 weeks or so.
Yeah, it's quite near.
Work. Yeah. Yes. So, yes, we have one question, please. Can you go to the previous slide, please?
Yeah, sure.
That the type asteroids are like 2 pounds or a modal more or less distribution, and if the statistic is very low. So do you expect to have a single peak, or maybe there are two kinds of peaks like the like for F and for G asteroids? Or
Okay, I didn't hear it clearly, but you were because it was
Perhaps
too loud, the sound.
yes,
Maybe
the B type, you have lower statistics, and
yeah.
they are like in 2 bunches. When you have more data, do you expect them to sort the gap or increase separately by model distribution, or was it like that, right?
Yeah, one of the things that we have we have some problems are in this region. Actually, for B types, we have a lot of problems in this region. So in this one, I don't trust this one. Probably this asteroid is not a B type. The classification is made kind of with an algorithm in which we transform the spectra to another set of filters in which the authors make a classification, right? So if we have a very noisy region in the spectra, it's quite difficult to classify some of them. Actually, for this one, I expect more that it is a P type and not actually a B type. In any case, what I expect, looking at the general trend of the B types, is that some of them could begin going down at 0.5 something, and but the big majority will be here, will begin here in 0.4.
Okay, so we'll see when you have more statistics.
Yeah, I need more data and less noise.
Okay. If there is, okay, thanks. If there's not any other question, we thank our speaker again and continue.
Thank you.